Welcome back. Got day 4 solutions. All right, we're going to talk about solutions today, why they form, how they form, and end up with Henry's law. So let's dive in. A solution. So a solution is a homogeneous mixture of two or more substances. So the particle size of a homogeneous mixture is usually less than a nanometer. A nanometer or smaller. If they're bigger than a nanometer, they become colloidal mixtures. They're heterogeneous mixtures like fog, right? And they don't separate on standing, and they can't separate by filtration. So you can't separate a homogeneous mixture by filtration either, right? Salt water, you can't separate that by a filter. Suspensions, such as when you start to get things over 1,000 nanometers or a micrometer, you can actually start filtering those out. It depends on your filter, of course. But we're going to talk about solutions with homogeneous mixtures that have particle sizes of less than a nanometer or smaller. All right. And so they can be in any phase. So it can be in any phase. Of course, that means it could be a solid, liquid, or a gas. Right? So that could be, dental amalgams that they don't use anymore, where there's mercury and silver. Right? Steel is one. You have liquids. You have solid and liquid, like salt water. You can have liquid and liquid, like ethanol and water, or denatured ethanol, where you have a little bit of benzene in the ethanol. Gas, air is a mixture. You can have water vapor and air. All right, so you can have all these different combinations. All right, and I think you guys know that. Now it's composed of two things. You have the solute and the solvent. So the solute is the minor component. What is being dissolved. So it's present less. You have less of it in terms of moles. The solvent would be the major component. What is doing the dissolving. So like the solvent for air would be water, or excuse me, the solvent for air would be nitrogen, right? It's mostly nitrogen, then oxygen, then argon, and then everything else, right? That's what air is. Over 99% of air is N2, then O2, then AR, right? Aqueous solutions is where water is the solvent. And this is where we'll live. We'll live pretty much in aqueous solutions. That's what we're going to care about. That doesn't mean other people don't care about what goes into the atmosphere or what goes into solids or metallurgy or any of that. Like we're not saying that's not important. Our class focuses pretty much on aqueous solutions. All right, and so now the next word we're going to define here is solubility. And solubility is the amount of substance that will dissolve per given amount of solvent. Okay, so for example, at 25 degrees Celsius, right, we end up with 36 grams of sodium chloride per 100 grams of water. And this is how we see it a lot of times, which technically means, by the way, that we have 36 grams of NaCl per 136 grams of solution. Right, so again, the units really matter. So a lot of times you'll see it 36 grams per 100 grams, but make sure we write the units so we know what we're doing. Now, we like to know our solubility. Solubility can also mean molarity, and we'll get there where it does mean molarity. But it can also be grams per grams. And why do we use mass? Well, pretty soon we'll learn that, obviously mass doesn't vary with temperature. Molarity does vary with temperature, so there we go. Alright, so now, the question says, what determines if something, right, some species, whether it's NaCl, whether it's the pencil you're holding, whatever you're talking about, what determines if something will dissolve? Right, have you ever thought about that? Right? We know table sugar dissolves. And we know it's based on temperature too. Right? We kind of knew this before we even did this. And my mom, she was wonderful. She is wonderful. She's still alive. My mom would, the three of us, I was the oldest, we had three of us, and we would make Kool-Aid, right? Because what kid doesn't like sugar drinks? And so she would make Kool-Aid. She would get a pitcher and fill it up 3/4 with water, put a bunch of ice in there, and then put all the, however much sugar, which was quite a bit, of sugar in this water, and make us stir it until the sugar dissolved, which is actually kind of mean, right? Because she knew that if you use hot water, sugar dissolves like this, right? It's real fast, and then you can cool it down. But she would do that, and it should keep us occupied for like 10-15 minutes, and then we'd probably lose interest, and then she'd just let it dissolve, and an hour later we'd have Kool-Aid. Right? So we know this stuff does temperature. We know that sugar dissolves. We know salt dissolves in water. We know sidewalk chalk doesn't dissolve in water, right? And it doesn't dissolve. It washes away from the sidewalk, but it doesn't dissolve in water. So what determines this? All right, and now the answer turns out to be intermolecular forces between a couple things: solvent and solute, so the solvent and solute, the solvent and solvent, and the solute and solute. Alright, so all these matter. Okay, now right, what do we mean by that? Okay, so they're all going to interact. So if you have water, and let's say you have salt, NaCl, because it's going to be simpler to use that. NaCl is bonded together, right? It's an ionic compound, NaCl, right? It's an ionic bond. Coulombic forces are holding it together. You got water, and that's a hydrogen bonded network of liquid. When we put the NaCl in the water, what's going to happen, right? Well, the sodium and chloride don't have a meeting, they don't talk, right? What's going to happen is the interactions between Na and Cl, right, are actually not as favorable as the interactions with Na plus, and then the water, and Cl minus with the water. And so it dissolves to a certain point. 36 grams of NaCl will dissolve for every 100 grams of water at 25 degrees Celsius. Okay, so when the solute and solvent interactions, or the solvent and solute interactions are greater or equal to, so we are greater than or equal to, right, solvent and solute spell that correctly, right, then the solution generally forms. Okay, just so you know, me personally, I learned a lot more about this in what was Chem 811. So we are in Chem 1. It's Chem 150, 151 here. Chem 101 most places, right? Whatever. So just so you know, that is a big difference. We're not learned more about this. So this is be pretty fine. We're going to simplify it even more. But when the solvent and solute interactions are greater than or equal to the solvent-solvent or the solute-solute, then the solution generally forms. And when the solvent and solute interactions are less than solvent-solvent and solute-solute, right, then the solution may or may not form. Right? So your book leads into this and mentions, right? There's a mention of entropy, which is coming much later. But because we're in day 4, that comes in like day, I want to say 24 maybe. So we have 20 lectures from now. Well, 18 because there's 2 tests in there. Right? And so entropy comes in, and this is the second law, thermodynamics. Right? But just so you know, that's the overall driving force. Okay. Okay, so what does it do? So the entropy is more of a disorder thing, and it sounds weird. We'll explain it more, right? It wants to, right? If we have so NaCl would be ordered. H2O is somewhat ordered. Okay? Alright? Basically these two things will mix. Right? Or, in this case, dissolve. To become more stable. Alright, that's what's happening. Things are going to mix to become more stable. It's actually a thermodynamic function that we'll examine later on. Okay, the key point is there's two words. There's miscible and immiscible. Okay, and so mixable means that they obviously mix, so it means that we will dissolve. So salt and water is miscible, right? Vinegar and water, miscible. Acetone and water, miscible. Okay, immiscible does not dissolve, not mixing. All right, and this goes back to like dissolves. Ooh. O-L-V-E-S. Like. So polar dissolves polar, nonpolar dissolves nonpolar. Okay, this is, you kind of knew this, right? If you were washing syrup, if you have syrup, sugar, table salt, if you have that on your hands, if you rinse them with especially warmer water, soap is really not even needed. All right, comes right off because water will dissolve those things. If you have butter or olive oil or coconut oil, whatever you're using on your hands, you need soap because the oil will not come off. Water will not dissolve it. Right? And so you guys kind of know this, that some things dissolve in water, some things you need other, right? You need either paint thinner, turpentine, right? We've used these chemicals before. Right? Nail polish comes off with nail polish remover. Doesn't come off with water. Okay? And so like dissolves like, and if it's polar, polar usually dissolves polar, nonpolar usually dissolves nonpolar. Okay, now it's not 100%, like chalk. Chalk, calcium carbonate, doesn't dissolve in water. That's okay. Alright, but even though it's on a compound, a polar solvent. So it's not always, but there we go, because some things aren't soluble. So now let's talk about the solution process. Solution process. Alright, how compounds dissolve. So this is the how. So how they dissolve. So we'll use an example of NaCl because it's simple. Alright, so I have NaCl, and that's a solid. And we know that we're going to add water, and we're going to add water. And there's something called delta H of solution. Right? So that, again, what's delta H? Enthalpy, heat transfer at constant pressure. Okay? So there's energy transfer here. And we're going to get Na plus aqueous plus Cl minus aqueous. Okay, what's happening? Well, this doesn't, how we calculate it and the steps we use is different than what actually happens, right? What physically is happening is different how we're going to calculate it. Okay. We have to break up the lattice energy, right? I don't know if you remember lattice energy. So lattice energy is the energy released when the ions form from the gas phase, right, to make a crystalline lattice. And so in this case, it's still going to be the energy required to break up the ionic lattice. And we get Na plus gas plus Cl minus gas, right? Because that's lattice energy is what we have, right? Does sodium go into a gas before it goes into sodium plus gas before it goes into sodium plus AQ? No, but this is how we're going to calculate it. Okay, and then we have solvation energy. Right, and then this is the energy released when ions are solvated. What is a solvated ion, you might ask? Right? So let's look at a solvated Na+. So when we say Na+, aqueous, it's really the same thing as Na H2O 6 plus aqueous. Alright? And so what do I mean by that? If I could draw here, draw a black circle. Alright. There's my Na. Well, octahedrally speaking, for the most part, there's going to be 6 water molecules. 1, 2, 3, 4, 5. Close enough. Right? And we know that the oxygen part of the water, right, with its lone pairs, will be around the sodium. So H2O. A lot of times we'll write it OH2 like that. Okay, the lone pairs are implied. I didn't draw them all. They're all there, though. They all have lone pairs, right? Electron density going to the sodium. So that's what a solvated ion is. It's usually 6 for these small ions. Obviously, bigger molecules have bigger waters. They have these solvation spheres, the inner one, the outer one. And it changes how the water is ordered. So it really does play a difference later on. But right here, this is what's all we're going to do. Now, the overall change in enthalpy upon solution formation is called the enthalpy of solution. Of course, we get delta H of SOLN, right? That's heat transfer, constant pressure. So, we know delta H of the solution depends on the magnitude of lattice energy and solvation energy. Alright, so delta H of solution, my delta H of solution can be negative, or delta H of the solution can be positive, right? If it is negative, if delta H is negative, we know that's exothermic, right? And it is enthalpy driven. If it's positive, it's endothermic, and it's not enthalpy driven. It's actually that entropy driven. Those words are very close together. So, alright. So, for water here. Alright, so for water, delta H of solution equal to delta H of the solute plus delta H of the solvent plus delta H of the mixing. Alright, so there's energy transfer. that holds us together. And so the solute, right, for water, what holds a solid together? The solute would be what holds the solid together. And that's usually going to be a positive number, right? Solvent, that's intermolecular forces, right, in the solvent. And breaking those up usually requires energy. And then mixing also has to do with intermolecular forces, and that's usually negative. Now again, everything can be, the overall could be a positive number and the thing can still dissolve. For example, ammonium nitrate energy is absorbed. It's endothermic. It happens. Alright. So the sign of delta H doesn't necessarily predict the direction of the reaction or the direction of the process. Okay. Now, factors affecting solubility. And we already talked about one, temperature. So, of course, temperature affects the solubility. And we know the solubility. So when I say solubility, I'm talking about how much dissolves. Right? How much dissolves. So how much dissolves, right? So the amount of, right, most solids that dissolve in water increases with increasing temperature. Alright? So for example, those of us who do dishes by hand, I always have students that do dishes by hand. Even they have a dishwasher, it's like a expensive drying rack for them. So, and I'm not picking on them. If that's you, that's fine. It's your dishes. You can do them however you want. My point is, they get, if you're doing dishes and you're using them by hand, hot water makes it's better. It's faster, right? That doesn't mean cold water won't work. In fact, I personally use not too hot of water because it hurts my hands. Right? My wife seems to be able to use some hot water. If I do the dishes, it's not nearly as hot. Rinsing the plates off, it can be hot, but not that hot for me. All right, hurts my hands. So, right, the point is, things dissolve better in the hotter water. Or they dissolve faster, right? So more will dissolve, and it dissolves faster. Okay, all right, and so we know that. So, just like there's a couple restaurants down here, Bojangles, one of them, Smithfield's, sweet tea. Their sweet tea, you can almost eat that with the fork. It's so thick, right? Because they get the water boiling, the tea's boiling, and they put all this sugar in and they cool it down. Unfortunately, now I don't drink iced coffee. I don't drink coffee. I drink coffee black. That's it. Hot coffee black. Doesn't matter the temperature outside. That's it. My wife will drink coffee, iced coffee, and it has cream and sugar. Well, they don't put the stuff in the coffee hot and then cool it down. It's cold down here, and it's just the cream and stuff, sugar just sits on the bottom, and it's not as nice. All right, it doesn't dissolve as well. And so we knew this. A lot of us knew this, that the solubility of most solids in water increases with increasing temperature. What we might not have known is that the solubility of gases in liquids decreases with increasing temperature. Alright, so this, if you have like a soft drink, drink soda, which maybe you do, maybe you don't. I'm not promoting it by any means. Soda, though, if you have that in your car and you let the soda sit there in the sun on a hot day. I'm originally from Michigan, where hot days did happen, but nothing like where I am at in North Carolina now. In the summertime, I've had ibuprofen melt in together, like the pills melt together, like one thing. It got so hot in the car. It was a black car, but still, and never had a problem. I mean, I'm from Michigan, where in the wintertime you could buy frozen foods and stuff and leave them in the trunk and go someplace else. You didn't have to go home. Right now, I'm from when you go to the grocery store, you better go right home. So, right, but if you have a soda in the car and that sunlight can actually warm up that soft drink so much that it can explode, right? That's all the carbon dioxide comes out of solution and causes the container to fail, right? So solubility of gases in liquids decreases with increasing temperature. The hotter the liquid, the less dissolved gas. The other factor affecting solubility would be pressure, right? So the higher the pressure of a gas over a liquid, the more soluble the gas is in the liquid. Alright, so this is how soft drinks are bottled, right? You can tell if a soft drink's fresh because you open it and you hear that tss, right? And so it's bottled under higher pressure of carbon dioxide. So Henry's law. With pressure, we get Henry's law. So the solubility of the gas is equal to the Henry's law constant times the pressure of the gas. Alright, so let's define some terms here. This is the solubility of the gas, usually in molarity. This is Henry's law constant, and it depends on three things: temperature, what solute we're talking about, and what solvent it is. And then this, of course, is the pressure of the gas. Right? And so what I mean is, if I have a container with a liquid in it, if I want whatever this gas is, if I want the gas in, I have to put more gas on top. So if I want CO2 in, if I want oxygen in, if I want nitrogen in, whatever it is, right? They're starting to put nitrogen into drinks now. All right, and so whatever we're doing, we want more of it above the gas, more goes in more above the liquid, more goes in the liquid. All right. Okay, so that is Henry's law. It's that simple. There's not much else. It's a very simple formula. Let's do an example of Henry's law. Determine the solubility of oxygen gas in water at 25 degrees Celsius exposed to air at 1.0 atmosphere. Partial pressure of O2 happens to be 0.21 atmosphere. Right, so what it will say is assume a partial pressure of oxygen of 0.21 atmospheres. Then the Henry's law constant happens to be 1.3 times 10 to the negative third molarity per atmosphere. So all we do here is use that formula. S of O2 is equal to KH times the pressure of O2. So S of O2 is equal to Henry's law constant, 1.3 times 10 to the negative third molarity per atmosphere, multiplied by 0.21 atmospheres, right? Because air is not all oxygen gas, right? It's mostly nitrogen. So if we did this, I get 2.7. This is my solubility O2, 2.7 times 10 to the negative 4 molar, which is not a lot, right? So when we take it in a breath, it's 21% oxygen. In this case, there's not that much oxygen in the water. So, right, breathing out of the water is probably not going to happen for us. And even though we've probably all been there thinking we could do it when we were like 4, not going to happen. So that is a solution process. That's why things dissolve. And we will see you next time.